but yeah, I would eat like we would go to there was a Costco that was walking distance.
Yeah.
I would we would eat their hot dogs and pizza a lot.
Yeah,
that was
for
our
$1.50.
that was our meals. So poor graduate. Okay, all right. So this is all bonus content. I don't know. I mean, bonus content not covered on the final exam. I guess I'll like in 101C I will talk about decision trees and whatnot. But I thought, oh, yeah, you know, it's a little bit like machine learning. It's not really. There is like an optimization aspect, but it's not. It's like a pretty simple. It's not. I wouldn't say it's like there's no like optimization algorithm type of thing going on. But it is like you know, decision trees are made this way, and then things like random forest are built out of decision trees. So anyway, that's what we'll look at today. And again, yeah, no view quiz. This is all just for fun. So yeah, a decision tree, basically you have all of your data, and basically it tries to kind of divide the data into different chunks. And the way, you know, it does it is basically it asks a question, and then based on your answer to the question, you go down, you know, these different paths, right? And so the tree at each of these kind of questions, or each of these splits, the tree uses just only one variable, and then at that split generally forms just a binary split, okay? And basically using some kind of rule, and so if, you know, this variable is numeric, it's going to be like, you know, is your value of x, is it bigger than some number or is it less than some number, is basically you know, what it's going to be. So it's going to be like, do you have high blood pressure, defined as, you know, your top number is 140 or higher, and then if so, you go down the right side of the path, and if no, you go down the left side of the path, kind of thing. Okay. And if it's a categorical variable, you know, it'll be like, are you in this group or are you in some other group? Okay. And if it's, you know, something complicated, it could be something like, are you in any of the following groups? You know, or like, you know, if we were going to split the United States, you can say, you know, are you from a coastal state? And that would be, you know, California, Oregon, Washington, and I don't know, whatever's on the East Coast, all of those states. Would we consider the South all coastal states too? I guess so. They do have coast. So, yeah. So you have the entire, right? Do you live in a state that touches the ocean? Well, that will be more clear. And then you can say, you know, yes or no type of thing. All right. And basically we just keep splitting, creating these partitions until we reach some kind of stopping criterion. And after all the partitions have been made, basically everybody within a certain terminal node, we might call this a leaf to keep the tree analogy going, just share a single predicted value. Okay. And so there are, and that predicted value can either be a category, and if it's a category, then we call it a classification tree. And if the predicted value is a number, it's a regression tree. Okay. But again, let's say you have a total of four levels of splits. You can have at most 2 to the 4, 16 unique predicted values, right? So for classification, you know, having 16 different values, that might be enough depending on your data, right? So you might have like maybe only like 9 categories, and, you know, 16 is enough to kind of hit them all. But if it's like a continuous variable and you're doing a regression tree, you are only able to make 16 unique numeric predictions. So there is quite a limitation as far as regression trees, but it'll be something like, if you answered yes to this and no to this and yes to this, we're going to predict your value is going to be, 17 or something like that. And, that may or may not be a good, good enough, okay, as far as what you're trying to hit. But we'll start off doing regression trees because I think it's easier to explain where we choose the splits. And then, classification trees, ultimately work similar, but just uses a little bit of a different kind of way to measure how right or wrong we are, okay? I should say decision trees, regression trees, classification trees, goes back to supervised learning in that, like, when you create your tree, you have answers, and so you're able to evaluate how good your splits are, how good your tree is based on that. So basically, when you create the tree, you're going to consider every single possible partition. Okay, so if you have a ton of data, modeling a regression tree can take a very long time, right? Because if you have like 1 million data points, it's going to consider every single possible split for, and so if you have 1 million unique values, there's basically 1 million unique locations, I guess 999,999 possible locations for one variable. And then if you have like 100 variables, you have to consider all 100 of them. But the way it works is it's going to kind of consider a split, and it's going to say, okay, how much improvement in RSS do we get? Okay, and it's going to just choose the one that minimizes the RSS. Okay, so it's greedy in that, like, it only looks at just at this one moment in time. Greedy's maybe, this is the term we use, but perhaps a better word would be like immediate gratification versus something else. So it's not able to kind of plan ahead. It just says, in this moment, what is the thing that's going to make me feel the best right now, and it's going to do that split. Okay, this is like a blast from the past. So this was in 2008. Okay, I don't know how old you guys were in 2008, but this was when Obama was elected president. But in the first half of 2008, there was the presidential primary, and there were several Democratic candidates, and so anyway, this is a decision tree that was published in the New York Times. And so one thing about decision trees is that they're simple enough for the public to understand. Okay, because it's kind of like like a little quiz or something. And so if you look at this, it feels so strange because today's political world is so different from what it was like in 2008. And so, but anyway, in 2008, Obama and Clinton were running to be the presidential candidate for the Democratic Party. And at this point, when this decision tree was created, several primaries had already happened. Several states already had their primaries, but there were still quite a few more primaries to go, and they were just trying to kind of predict, okay, if we look at what's going to happen in the future, who might win. And so they ran some data, and they said, looked at things like race and high school education and things like that. And basically using this, they would make a prediction as far as who would win the county during the primary. All right, and so if it was if the county was more than 20% black, Obama won those counties. If the answer was less, if the answer was no, then the next question was, is the high school graduation rate higher than 78%? Okay, and if the answer was no, then Clinton would win those counties. But then if the high school graduation rate was higher than 87%, then Obama won those counties. Whereas the county in the Northeast or the South versus the West or Midwest, were many households poor, yes or no, and things like that, right? So it's kind of interesting because if you did not know, Clinton was the, what face you would put over here, and you just kind of read these questions, I think we would probably think it was like a different person. But anyway, that was a decision tree that actually got published in the New York Times, and I thought it was kind of neat to see, one of your statistical applications show up so clearly in in a public kind of public setting there. Generally you only see like bar charts as far as data graphics go. Like a scatter plot is fairly rare to see in a newspaper. Maybe, academic reports and journals, yes, scatter plots, but in a newspaper, I don't see them very often. Generally just bar charts. And that's our level of data literacy in the public, so. Okay. Well, anyway, so what we're gonna do is we'll create a regression tree ourselves for this very, very, very simple toy data set, okay? Just to kind of illustrate. All right, so our X values, we have 1, 2, 3, 4, 5, and then our possible values for Y are 1, 1, 3, 7, and 8. And we're gonna say, all right, where should we create a split so that we get kind of our best predictive performance as far as the regression tree goes, okay? And so we start off with kind of the base case where we say, okay, well, we have no partition. If we have no partition, then we would just predict one value for everyone. And the best value to predict, that's going to minimize your residual sum of squares is the mean, right? Do we learn this? That the mean is the value that minimizes your sum of square deviations, and then the median is the one that minimizes your sum of absolute deviations. So, but the median is not doesn't have a unique solution, but the mean has a unique solution for these things, generally speaking. So, okay. So anyway, we put in the mean. So what's the mean of 1, 1, 3, 7, 8? We get 4, and then the RSS is going to be 44, right? So we do y minus y hat squared, and we sum them up. So 1 minus 4 is 3, 3 squared, 3 squared, 1 squared, 3 squared, and 4 squared, and all of that adds up to 44. So this is going to be our baseline. Any split that we do should improve this. And that's basically like when you calculate your R squared values in like regression. Did you know it's possible to get a negative R squared in certain models? And that's like if your model, so it happens when you do cross validation. So like, so when you do cross validation, you might, your model might say, okay, this is kind of the split we should make or something, or the predictions we should make. And it turns out that when you take that model and apply it to your test set that wasn't observed, that your predictions are so bad, it would have been better to guess the mean for everybody. And if that's the case, you end up getting a negative R squared value, right? So it's like, we would have been better off if you didn't come along type of thing, right? But if you overfit your data so much that, when you do make predictions for your test case, there are sometimes situations where it's like, we would have been better off if we just guessed the mean for everybody. It's kind of like on a multiple choice quiz, if you just guessed randomly, you should hit 25%, and then if you actually or like read the questions and you do worse, that would be a situation where you get negative r squared, right? Because the baseline is that. So anyway, okay, so this is our baseline. We're predicting 4 for everybody. We square all of these differences and we get 44. Okay, so we're going to consider all possible partitions. So we're going to say, all right, we're going to split between x is 1 and x is 2. So we'll create a split at like 1.5, x at 1.5. And then so we have, on partition A, there's only one value. So what do we predict? We're going to predict 1. We have no residual on that side. And then for the other 4 values, we have 1, 3, 7, 8. And so the average of those things are 4.75. And we say, what is the RSS here, right? So no residual here. A bigger residual here, smaller residuals over here. And then when you square all of those residuals, you get a 32 RSS of 32.75. Okay. Trying the next split. Okay, we'll split after at x is 2.5. Okay, greater, for values less than 2.5, we predict 1, and so we have no residuals on this side. And then over here, the average of 3, 7, and 8 is 6. And so when you predict 6, you get a residual of 3 squared, and 1 squared, and 2 squared. And so that adds up to RSS of 14. Here we'll split between 3 and 4. And so the average of 1, 1, and 3 is 1.67. And then you can square those differences. And then up here we have 7 and 8. The average of those two is 7.5. And we square these kind of residuals. And so the RSS of this split is 3.1667, which is pretty good. And then we'll consider one more split, and we'll say, okay, now we're going to put split between 4 and 5 on x. And then, and so these are, our predicted value here is 3. And so we have, residuals of 2 and a residual of 4 here, and then no residual there. And then when you square all of those things, you get an RSS of 24. Okay, so kind of reviewing all of these things, we probably could have guessed just by looking at the data, but when you look at these charts, we can see, okay, the one that's going to minimize the RSS after the split is going to be this one, and that's the split that we're going to pick. Okay, and basically all of your like for a bigger data set, you do the same thing, just you just have a whole bunch of splits to consider. So if you have so if you have 100 values and 5 variables, you'll consider basically you have 99 locations for variable 1, 99 locations for variable 2, 99 locations for variable 3. You're going to consider all almost 495 possible splits, and then you evaluate the RSS after every single one of those splits, and you say, all right, this is the best one out of the 495. There's possible that you get a tie, but probably, and then in that case it doesn't really matter. But generally, out of you say which of the 495 splits performed the best, and that's going to be the one you pick. Okay. So we do this. We could do this in R as well. There is library R part. There's also library tree. And then when I teach 101C, I use the Tidy Models package, and that can employ a bunch of stuff, including R part, and then even a faster performing thing. Actually, rangers for random forest, like a forest ranger type of thing. But our part will create a decision tree. And so we do library R part, and you just call R part formula much like you would call a formula for LM, and then data, the data set, and then there's some control things here. So we'll just do y tilde x, and then by default Control will have things like, we'll say like, okay, this is like when you put your stopping criterion in, like how many levels of tree do you want? What's the minimum number of observations that you need to have if you're going to consider a split? So a lot of times your stopping criterion will be like, okay, once you get down to like 5 observations in a leaf, like don't try splitting that any further, because you'll end up with too many leaves and overfitting your data. But because I've got such a tiny little data set for my toy example, I have to change the control. Okay, I think the default is minimum number of observations to consider split should be 20 observations, but we're going to say minimum split is 5 because that's how many observations I have here. So I just do, here's our data frame, x is 1 through 5 and y is 1, 1, 3, 7, 8, and then we're going to say our part y tilde x. Our data comes from the data frame, and the control is we're going to say minimum split 5. And here it says make the split at x less than 3.5 and x greater than or equal to 3.5, which is exactly what we came across. And there's other information here that matches the information that we encountered. So the very kind of top line, it says, you had 5 observations that we are gonna split, okay? And so here it says, you're gonna end up with 3 observations on this side and 2 observations on this side. The deviance, which is kind of our residual sum of squares, is 44, and the predicted value is 4.0. So this was kind of what we had at the very beginning, where we said, okay, if our values are 1, 1, 3, 7, 8, our predicted value is 4, and then when we do our RSS, we get 44 there. Okay, so that's this top line. As I have it all broken down here, and then the next line says, okay, when you're going to form the split when x is less than 3.5, you're going to end up with 3 observations there, and then this is the predicted value for those 3 observations, and then your RSS for those 3 values is 2.667. Okay, so it's this thing. So we're saying draw it at 3.5, so make the split here, and then if we added these up, 0.44, 0.44, and 1.77, we would get this same number of 2.667. Okay, and then over here it says for these 2 observations, your predicted value is 7.5, and your RSS is 0.5, 0.5, right? 0.25 plus 0.25 for those 2 deviations add up to 0.5. So a lot of the same kind of information, but just summarized in the tree. This is a very kind of small, trivial tree here. You could also call summary. Okay, summary on your resulting tree. And this first column is complexity parameter. Basically, it's kind of like a R-squared value for that particular split. The primary split is going to be at x less than 3.5, and here it says your improvement is going to be 0.928, right? Or your complexity parameter here is 0.928, right? And the way we calculated that value, 0.928, was before the split, our RSS was 44. After we do the split, the total RSS is 3.1667, right? So before the split we had 44, and then after the split you add these 2 numbers up, you get 3.1667. That's a reduction of 40.83. 40.83 is 90, around 93% of 44. So that's how it calculates its kind of, R-squared value here, or the complexity complexity parameter value here. Okay, or improvement rating. This is stupid, but you can. There's a plot function for the tree. This is the dumbest little tree with just kind of one split. So it just shows. Yep, on the left, your prediction value is 1.667, and on the right, your predicted value is 7.5. Okay, so you actually, if you do plot without text, you just get the line. And then you have to add text to give it any information. And so here it says, okay, the question is x is less than 3.5, and if the answer is yes, we're going to predict 1.667, and if the answer is no, we predict 7.5. So remember, regression tree, if you have two terminal nodes, you're only predicting two values. So it's, for this toy data set, we just say, it's kind of like, I don't know. You ask somebody, how old are you? Okay, if you're under 25, we're going to predict your car insurance is $1 million, and if you're under 25, we're going to predict your car insurance is super high, and if you're over 25, we're going to predict your car insurance is super low, or something like that, right? You're only just predicting two values, and obviously individuals within those kind of things are going to be quite different, but that's just what we have. So if you had a more complicated tree, the plot of the tree would be a little bit more informative, a little bit closer to, something that looks like this. But yeah, you can do this. There are additional packages that you can run in R that creates prettier looking trees. You can create your own tree somewhere else, right? Okay. Okay, I already said this. For a larger data set, it would kind of consider all of these all of the possible partitions across all of the possible variables, and it will just pick the one split that performs the best. It doesn't do a look ahead. I think there are some kind of algorithms that would consider maybe like looking ahead, like picking a non-optimal split here so that you can achieve a better split later. But it's like really computationally expensive because now you have, if we, with this kind of small, not even a huge data set, right? 100 values, 5 variables, you have 495 splits to consider. And then you would have another kind of 495 values, or maybe even more than that. So basically, it just grows very rapidly in terms of how many splits you have to consider. So, but anyway, after you split the data, so let's say you find this spot and it partitions the data into, you have 100 values, and it does a 60-40 split. So you say like, okay, is X greater than this? And it, the answer is going to be yes for 60 and then no for 40. So now you have 60 observations and you're going to say, okay, what's the best possible split for these 60? Okay. And then you do it and maybe you find a split that does like 20 and 40 or something. And then you say, okay, what's the best possible split for these 20? And then once you reach your terminal condition here, then you go kind of climb back up the tree and you say, okay, well, here's these observations of 40. What's the best split there? You keep doing that. And then finally you come back to the last one because the very first split was 60-40. And then you say, okay, these last 40, what's the best possible split there, right? So you kind of do it recursively down kind of one end until you reach the end. And then you kind of climb back up the tree and you go back, okay? Sometimes if you just follow the kind of recursive algorithm to the end, you end up with an overly complicated tree. And so we might consider pruning the tree. I guess we really love this tree analogy of growing things. And so, a lot of times you might have, a tree that overfits your data. You have some unnecessary partitions, and we'll consider removing some of these partitions, okay? And so here, the R part control is, just kind of make a split basically everywhere. You need just two observations for you to consider a split. And if we do this, I end up with 4 terminal nodes, which well, I had 4 unique values in y. So I have a terminal node for every unique value, right? So we said, okay, if first we split at x is less than 3.5, and then if it's less than 3.5, consider another split at 2.5. And so basically, we're going to predict 1 here. We predict 3 for any value between 2.5 and 3.5. For any value between 3.5 and 4.5, we predict 7. And for any value higher than 4.5, we predict 8. Okay, and we have no residuals because we're predicting every single value in our data correctly. All right, and this is not a good plan because well, anytime you get 0 residuals, you should be highly suspicious of your model. And anyway, yeah, with only 4 unique values, we could have at most 4 nodes, and yeah, we're getting everything correct here. So to kind of decrease this overfitting, we would prune the tree. And so pruning the tree, we remove the weakest link, the weakest branch or weakest split one at a time until we reach the tree that looks like what we want. Okay, so what we'll look at is we'll say, okay, our first split was at 3.5, and then we had 2 following splits. We had a split at 2.5 and a split at 4.5. All right, so which one is kind of the less important split? Okay, well, basically we say, well, how much RSS did that split do? So the split at 2.5, prior to the split, we had an RSS of 2.667 on that side of the tree. After the split, we brought our RSS down to 0. Okay, and then the split at 4.5, prior to the split, we had an RSS of 0.5. After the split, we have an RSS of 0. So our improvement here is, from 0.5 down to 0, and our improvement goes from 2.66 down to 0. So this one has less improvement than this one over here. Okay, so that's kind of how it goes. The how much improvement did we get? So it went from 0.5 down to 0. So our improvement would be 0.5 divided by the total RSS at the beginning of 44. So 0.5 divided by 44 is 0.0114. Okay, and then over here, our improvement goes from 2.66 down to 0, a total of 0 here. So our improvement would be 2.66 divided by 44. That's an improvement of around 6%. Okay, so so kind of our complexity parameters here. These are kind of the improvement numbers. The first split reduced RSS by 0.928. The next split reduced it by around 6%, and that final split reduced it at 0.0113. And then this last line of 0.01 is kind of like the tree would only consider a split if the improvement was at least 1%. And in our case, like all of the splits hit that thing. So, so this is kind of like your baseline thing. So anyway, we look at this and we say, okay, well, this is the weakest split here. And so that corresponds with a complexity parameter of around 1%. And anyway, that's the one we would do, right? So here I'm going to say prune the tree, and we're going to say the minimum kind of improvement, the complexity parameter has to be at least 2%. So it will kind of eliminate this bottom one, and then so we have the split at 3.5, the split at 2.5, but we no longer have a split at 4.5. Okay, and then if you increase your complexity parameter even further from say 2% up to 10%, then you get the kind of tree that we pruned back that we saw at the beginning here, where we got rid of kind of these additional things. So obviously for the toy example, it's not super interesting, but you can apply this, and that's what we have. there is a, so how do you decide where you should prune your tree and stuff? Well, you can use kind of cross-validation. And so in our part, they have this kind of 10-fold cross-validation, or I mean, you can choose whatever number of folds, but that's, I think the default is 10 folds. And what it will do is it kind of it fits a bunch of these trees. Okay, so it kind of takes it builds out this complex tree. Let's say you end up with like 8 branches or 8 nodes, and then it says, okay, we're gonna prune back the tree down to 7, down to 6 nodes, or 6, 5, 4, 3, 2. And it says, okay, with these 8 nodes, right? So with 10-fold cross-validation, you use 90% to kind of train it, and you get your 8 nodes. And then you say, all right, let's make predictions on these last 10, okay? And then it does this for all kind of 10 folds, and it says, okay, if we say we're going to make a tree with 8 nodes, or using this complexity parameter, what's the average kind of test error do I get, right? Okay, now what if I take my tree and I cut back down to 7 nodes, right? And we're going to say, all right, we're going to go 7 nodes, we're going to train it on this data, make a prediction over here, train it on another thing, look at this data over here, how much, what's kind of the average error that we do there, and it kind of goes all the way back down to 2 nodes, and it says, okay, when you only have 2 nodes and you train it on 90% and predict on the last 10%, how much error do you get? So you're going to get a little bit of different error. You get a kind of I guess a standard deviation there, and then and so it says which tree produced the minimum kind of cross-validation error, and then what other trees produce similar levels of cross-validation error, okay? And it says, okay, let's look at, one standard error, and then, what other trees produce a cross-validation error within a standard error here. So I looked at data from, I guess, this CARS data set, cu.summary data set, and I don't know when this data came from, but this is like predict the price of the car based on what kind of mileage it gets, what type of car it is, what country of manufacturer is the car, and I'm not familiar with these cars because I couldn't name a single brand of car that comes from Brazil. They make cars, and I just, in the U.S., I don't think we have any Brazilian brand cars. I don't even think we have any French branded cars in the U.S., but you've heard of like Renault from like, when you watch a movie that takes place in Europe or something, right? And I guess like, so you have Renault and I don't know other French cars. I was gonna be like Fiat, but Fiat's Italian. So, okay, and then you have Japanese cars, Korean cars. Oh, I don't know, Mexico? I know there's a lot of cars produced in Mexico, a lot of factories. I don't know. Okay, so maybe this is country of production, maybe not even the brand of the car. I'm not even sure. Okay, well, anyway. We'll say, make the split. If it's either a compact, small, sporty car or a van, you predict this, 13,000. And if it's a large or medium car, you predict 21,599, right? So this must be like decades ago, because you're never going to find a car for this price new. Yeah, okay. So anyway, these are the kind of the different levels of tree size you can have. Tree with 7 nodes or something, and different kind of complexity parameters. And this is our best performing tree. Okay, this, and so the complexity parameter of 0.026, this produced the smallest cross-validation error. And we have error bars on here, okay? And so actually, as we went to 6 or 7 nodes, the cross-validation error went up. But if you go from 5 down to 4 nodes, the amount of cross-validation here is more than 1 standard error away from the minimum cross-validation error. So our minimum cross-validation error for this run is happened with 5 nodes, and that would be the kind of the size of the tree that we would pick. I think I ran it again. We got kind of the same results. Let me see. Oh, maybe my randomness came out different. Okay, so yeah, we ended up with 7 terminal nodes, but okay, so well, if this graph had this dot underneath this horizontal line, and again, these are just arbitrary kind of guidelines, but if this dot and this circle ended up below the horizontal line, we would consider creating a tree of complexity 4, because even though 4's amount of cross-validation error is higher than that of 5, if it's within 1 standard error, we'd say, you know what, maybe that difference isn't significant, and so it's okay. Again, kind of an arbitrary rule or a guideline there, but that's what this horizontal line represents. It says, okay, your minimum cross-validation error happened at this location. This is 1 standard error higher than that minimum cross-validation, and pretty much anything, it sees it as like, fairly equivalent. You're not getting that much improvement there, okay? And both of these, in this one, and again, because it's cross-validation and there's randomness, you might want to consider running it multiple times, because things are random and you end up getting different results, right? That's one of the disadvantages of k-fold cross-validation, is that it's subject to randomness. So, you run it again, but we got similar results again, okay? The lowest happened at 5. 4 came really close to being under that line. So, it really comes down to, do you do 5, do you do 4? Are you okay with a little bit more cross-validation error? Do you want the minimum cross-validation error? And we see going up to 6 or 7 actually kind of doesn't really improve the performance. And if anything, maybe it makes it worse. Right here, it looks like the performance isn't dramatically different, but why make it more complicated if you're not going to get any improvement, right? So we really just want to make things more complicated if we're getting improvement. It seems like we're getting just enough improvement when we go from 4 to 5 to kind of justify keeping 5, but we're not going to see any more improvement when we go to 6 or 7. And so that's how a decision tree works. Decision trees by itself, you don't have great performance, because again, even if you're asking like a bunch of questions, you might end up with 7 terminal nodes, and to be able to predict only 7 unique values probably is not the greatest. So we improved decision tree performance by doing things like random forest. Maybe I'll talk about random forest on Friday or something. And but yeah, so there's a lot of things that we like about a decision tree, and then we kind of improve it by creating forests, or we do boosting, or we do all kinds of stuff. So yeah, XGBoost is a very popular kind of machine learning algorithm that basically employs decision trees, but like a whole bunch of them that have been like adjusted. So okay, we'll wrap it up here. Thanks for coming. And those of you who are watching, thanks for watching. I know there's no view quiz, But I don't know, maybe you learned something. All right, well, maybe we'll see you later. Okay.